Your talk.
I'm only going to say good things about you.
Okay,
I'm
well,
going to
that's
switch to
good.
Spanish.
Bueno,
Okay.
vamos a empezar el coloquio del día de hoy, extraordinario, de un proyecto pues relevante, nuestro observatorio. Entonces, para hacer una presentación más adecuada, pues Mauricio tiene la palabra.
Gracias, gracias. Bueno, pues hoy, el día de hoy tenemos el gusto de tener con nosotros a Matt Lehner. Algunos de ustedes pues ya lo conocen, viniendo por aquí desde hace pues casi 13 años, ¿no? 12, 13 años. Les comento brevemente, Matt estudió física en la Universidad de Washington, en St. Louis, por allá en el 88. Después hizo su doctorado aquí en San Diego, en la Universidad de California en San Diego. Y su área de especialización fue en materia oscura de partículas. Participó en el proyecto Macho por varios años. De hecho, hizo un postdoc en Inglaterra como parte de este proyecto. Y por ahí del año 2000 se empezó a meter en la cuestión de los transneptunianos y lo contrataron en la Universidad de Pensilvania, después en el CFA y en Harvard. Y finalmente, en 2008 es Research Fellow en el Instituto de Astronomía y Astrofísica de la Academia Sinica de Taiwán, donde también es el Project Scientist para el proyecto TAOS 2, que es de los que nos va a platicar ahorita sobre su estatus y, bueno, pues ya el inicio de operaciones esperemos ya muy pronto, sobre todo las formas en que nuestra comunidad puede aprovechar este proyecto. Adelante. You just said that you're a nice guy.
Oh.
Or you can ask me later.
Yeah, I'll find out later. Is there a microphone or am I being picked up?
Yeah,
It's all
you're
good.
being picked
It's
up.
environment.
Okay, so. Get oriented here. So I'm sure a lot of you have heard of this project before since it's at San Pedro, but I'm going to talk about TAOS 2, the Transneptunian Automated Occultation Survey. It's obviously what the 2 implies that it's a second generation survey. The first version was at Lulin Observatory in Taiwan, which ran roughly 2004 to 2011. It was a much smaller survey. We didn't find any events, which was not unexpected. But we learned a lot about how to do this right, and also a lot about how not to do it. So this is a collaboration between ASIAA and Taiwan, UNAM, you guys, the CFA and the NRC in Canada, in particular the Canada Astronomy Data Center. So that's the outline of the talk. I will review. I'm sure this is a review for a lot of you people, but I will discuss the science goals and the requirements for the survey to meet those science goals. I'll talk about the survey infrastructure, and then I'll talk a little bit about the data, how it's structured and what we can expect from the survey. And the main purpose of this talk, I'm sort of in the middle of a little visit to all of our collaborating partners to try to encourage people to consider using this data for other science. It's going to be a very new and unique data set, and there should be a lot of science that we can get out of it outside of the occultation survey itself. So TAOS 2 is a blind occultation survey for faint trans-Neptunian objects, which are just small bodies orbiting out beyond Neptune. There have been a lot of occultation measurements done in the past. Usually these are targeted, so some minor body will be predicted to pass in front of a star. People set up their telescopes. This is very useful. A lot of the targets for the upcoming Lucy mission, for example, which will look at Jupiter, go visit some Jupiter Trojans, they've been doing a lot of occultation measurements of those objects. This will help constrain their orbits and see what they can expect when they get there, and also possibly search for satellites, which would be good to know if you're flying a spacecraft by an object. We're going to take a different approach. We're just going to monitor a lot of nearby stars and just look for a temporary drop in the brightness of the star and just randomly try to find occultation events as they happen. And the goal here is just to measure the size distribution of Transneptunian objects with diameters roughly in the range of 200 meters to 30 kilometers. The lower size limit here is set by the sensitivity of the survey. You really high signal to noise as you get to smaller and smaller objects. And this upper limit is just set by the smaller number of the larger objects and the total number of stars we can look at any given time. So there's a number of reasons for doing this. One is just to find the source population of the Jupiter family comets. We know there are a lot of objects floating around Neptune. There are several thousand have been discovered to date, but they're very large objects. They're much larger than the comets that we see. But so these objects are orbiting around, and every once in a while, the orbits will get tweaked by some like an interaction with Neptune or a dwarf planet. A lot of them will get ejected, but some get pushed into the solar system, and they kind of bounce around in these unstable orbits between Jupiter and Neptune. But every once in a while, they'll get pushed in toward the sun, and then those are the comets we see. So we believe there's a large number out there, but we don't really know how many, and we don't really completely understand the mechanism by which they get their orbits get perturbed into the inner solar system. So by measuring the size distribution, we can help constrain those models. Also, we can the size distribution reflects the collisional history and the internal structure of the TNOs, whether they're solid blocks of ice and rock or more loosely bound gravitational rubble piles, as they call them. So when the solar system formed, the models show that it just was a nice smooth disk, and as these things coagulated and bodies formed, there's a nice power law distribution, but it doesn't really stay that way. There's a lot of evidence that the giant planets moved around quite a bit, and in particular, Neptune is believed to have been formed at 20 AU, but it's moved out to about 30 AU. And as that happened, it pushed through this belt, stirred a lot of things up, and this, and as that stirring process occurred, a lot of the smaller objects started colliding and breaking apart. Depending on the structure, they broke into big pieces or smaller pieces. And then longer time scales, larger objects would start to collide more frequently. And you would expect this to have a big rough break in the power law distribution. And we see this break about 90 kilometers, but things below there are not very well constrained at the time. So by measuring the size distribution down to such small diameters, we can help constrain the models of the solar system formation and evolution. So just to show the sensitivity of, or the expected sensitivity of TAOS2, this is a plot of all the known TNOs that were in the Minor Planet Center database about 6 months ago or so when I made these plots. On the left, they're plotted at their perihelion distances, and on the right, they're plotted at their semi-major axis distances. So you can see there's a lot of objects out here at larger semi-major axes, but all of those were discovered much closer to their perihelion distances. So this red line, this is a contour of constant magnitude and reflected sunlight, assuming an albedo of about 4% of these objects. And this is at magnitude of 30. So anything beyond this region is going to be, any objects out here will be invisible to direct detection. They're just too small and too far away. We're looking at light and reflected sunlight. So that goes as the square of the diameter, but it also goes as the distance to the -4th power, because you get a 1/, distance squared from the sun going out to the object, and then another distance squared coming out to the observer, which is roughly at the same distance. So There's a survey ongoing right now with using the James Webb to try to find these objects, and they should be able to push down to about 10 kilometers, but they're not going to get beyond this line here. So the TAOS 2 sensitivity is going to open up all this parameter space. This is set by the black line here. That sensitivity is roughly defined by these two dashed lines. The green dashed line is the Fresnel scale at visible wavelengths. And if your TNO is occulting a star near or below this line, instead of just a geometric shadow, you're going to have some significant diffraction features. And as you get further and further below this line, your event will get shallower in depth until it's just lost in the noise. This blue line here is the angular diameter of a typical target star projected to the distance on the x-axis. So if your TNO is below this line, you're only occulting a fraction of the starlight. It's like an exoplanet transit, except it's within our own solar system. It's much smaller than the size of the stars we're looking at. So you get down below there, you're going to lose the signal into the brightness of the star. So our main science goal is to get down in this region here for the Kuiper belt, but we actually can go out a lot farther. There's quite a few objects out here which are very puzzling, and it's mostly puzzling because there have been so few of them detected, and we don't really know what they are or how they got there. So it's sort of a side project we're going to be looking out here to see what we can find. But this talk will concentrate on the TNO region. Yes.
Yeah.
Oh.
Sorry, what is the difference between the left hand and the?
Oh, sorry. So this is the perihelion distance.
Ah.
This is the semi-major axis. So these guys here have very eccentric orbits. Their perihelion distances are much closer to the rest of the Kuiper
They
belt.
are the same objects. but
Same objects,
different
just, yeah.
position. And another question.
Yeah.
How would be the lines, the sensitivity lines for the TAOS 1?
TAOS 1 had the same shape, but it was much,
Shallow.
it was a little bit higher. Yeah. So it was about up to, I mean, the metric here is we're good about 200 or 300 meters here. TAOS is down to about a half kilometer, but that's just the very limited, which you can see. Your detection efficiency there is very, very low, but we expect a lot of objects in that regime as well. So you're multiplying a very large number by a very small number, and yeah, hoping to get a few events. So this is to show what we're looking at here and to give some scale of what we're trying to see. This is a shadow of a 3 kilometer TNO occultation. And the scale here on the bottom, it's about 10 kilometers by 10 kilometers. So if you imagine just one star and one 3 kilometer TNO, this is the shadow you would see on the surface of the Earth. And these things are in relative motion to the Earth, mostly due to the Earth's motion around the sun. The TNOs themselves are moving very slowly. And so hopefully one of these passes over your telescope, you just measure some chord through the shadow. So this width is set by the Fresnel scale once you get down to the smaller objects. So the Fresnel scale is just the geometric mean of the wavelength and the observer TNO distance and 0.5. And if you're looking at 43 AU and 600 nanometers, that comes up to right around 1.5 kilometers. And this sets a minimum event width, which we're defining as the diameter of this large Airy ring here, this first Airy ring, at 2√3 times that, which is 5 kilometers at 43 AU. So you can see roughly the scale there. Now, the relative velocity, as I mentioned, that it's mostly due to the Earth around the sun. The relative velocity at opposition is 25 kilometers a second. So you do the math, when one of these passes over your telescope, the time scale will be about 200 milliseconds. So you need very high cadence observing to be able to see these shadows. Now, if you are off of opposition, it tends to go slower, so it stretches the event out a little bit in time. So just to show you what we might measure. So we will operate at a cadence of 20 hertz. And I got a few different things here to just illustrate how the the physics, the size and the distances will affect the light curve shapes. So at the top, I have something in the Transneptunian belt. I have a 1 kilometer, 3 kilometer, and a 30 kilometer. And the red lines are at opposition. The blue lines are 60 degrees from opposition, where the relative velocity is down by about a factor of 2. So for the 1 kilometer guy, you can see there's only about 5 data points in there, but you can see this, the 2 little high points for the area ring and then the Poisson spot in the middle. As you get out to 60 degrees, it's roughly half the velocity, so the event is twice as wide. Now, if you go up to 3 kilometers, you can see the event width is roughly the same. This is just because you're in this diffraction dominated regime where this minimum event width comes into play. And so instead of getting wider, the event gets deeper. And then it works in the opposite direction. It works the same way. As you get smaller and smaller, this event gets shallower and shallower, even though it stays the same width. Once you get out to 30 kilometers, you're in the more geometric shadow regime. You still see the diffraction spikes here for the area ring and a little bit of the Poisson spot, but you can, aside from those points, you can model this very passing one circle in front of another circle and calculating the light curve that way. So these are harder to detect. So you need higher signal noise stars. There are a lot fewer of those, but we expect many, many more small objects in this range. Out of 30 kilometers, they're very easy to detect. You don't need very high signal noise in your star, but there's also a lot fewer of the objects. So the sensitivity will peak toward the smaller end, but we're still sensitive out to these objects. So the other thing, as I showed a couple plots ago, the angular size of the star becomes important, especially as you go out to larger distances. So these are objects would be like sednoids, which are objects out in the Sedna regime, which is a dwarf planet with a semi-major axis of around 400 or 500 AU. So here the red line is a magnitude 17 star, and the blue line is magnitude 12 star, and same spectral type. So the magnitude star 12 is a lot closer, so it has a much larger angular diameter. And again, you can see for the smaller star, it's rough. You can roughly model that as a point source. It looks similar to the events above, but it's wider, and that's because the Fresnel scale, if you recall, goes as the square root of the diameter of the distance to the object. So in that regime, in the diffraction regime, the events get wider as you go further out. And then if you go up to a 5 kilometer, you can see the event gets deeper, similar to what we saw above. And then out of 30 kilometers, again, you have roughly the geometric shadow shape. But if you go to the larger angular size, you have to integrate this diffraction pattern over the whole star, and that averages out most of the fringes, and you get this sort of V-shaped pattern. So that's sort of what limits you as you get to smaller and smaller objects out in this at larger distances. So for the requirements of the survey, we need a lot of data. These events are rare, like one per 1,000 stars per year, if you're depending on the size. So you need a good site, for many clear nights and good observing conditions, which is why we're at San Pedro. So we need to photometrically monitor a lot of stars. Our goal is somewhere between 5,000 to 10,000 stars on average, depending on the field and what part of the sky is up at any given time. So you need to go to some combination of a wide and deep field. We want to do 20 hertz imaging to resolve the events. So we're using these modern state-of-the-art CMOS sensors that will allow you to do multiple subframe readout around the stars. Our cameras are 88 megapixels, and trying to read that out at 20 hertz and save all the data would be an impossible task. But by doing this multiple subframe readout, we can get the data rate down to 1% or so of the full frame, which makes it actually possible. We want to minimize the false positive rate. We might expect 10 to 1,000 event per year, depending on what the size distribution is. But we'll be doing on the order of a trillion photometric measurements every year. So the odds of some star wiggling a little bit that might look like a occultation event are probably pretty high. So we're going to require coincident detection in multiple telescopes. So that should get the false positive rate down pretty low. And we expect one of the, for single telescope data, we expect the thing that's most likely to mimic an occultation event is a scintillation event in the upper atmosphere. If you get like 100 meters or so separation, then the 3 telescope view of the same star will be looking at different parts of the atmosphere. So that should minimize any of the scintillation and false positives. I don't think I need to cover this, but yes, SPM, very dark site. Very good seeing. Google Earth view of the 3 telescopes. The separation, the minimum separation is 127 meters. North-south, it's a couple hundred meters, so we're far enough apart. I'm sure you've seen this too. This is the 4th time I've given this talk in 5 days, so some of these slides are probably not relevant to you guys, but anyway, so this is a picture of one of the telescopes. The 3 telescopes are identical. They're from DFM Engineering in Colorado. They're f4, 1.3 meter diameter with a single Schmidt corrector plate near the Cassegrain focus to kind of flatten out the field a little bit around the edges. This is the same model as the 1.3 meter telescopes at Mount Hopkins and the USNO, or it's the f4 version of the Ogle telescope. If you're familiar with any of those, it has a 1.7 degree field of view over 154 millimeters, and we're expecting a limiting magnitude of around 17 at 20 hertz. We're still working to finish up our collimation on these 3 telescopes, so we'll see how faint we can really push this. Our target for limiting magnitude, we're going to call signal noise of about 1.2. That's not great, but it's good enough for the 20 to 30 kilometer objects where there might be 15 to 20 measurements throughout the event that are at 100% flux drop or near that. So putting that together a little bit, you should be able to pull these events out pretty easily. And this is enough for getting close to our target of 10,000 stars. Where we don't expect to get that every night. There's going to be some nights where the ecliptic is really far away from the galactic plane, and there just won't be that many stars there. So we finished the installation of these telescopes in 2017, and then we still had to finish putting the cameras together, and we had a little problem with COVID, which set things back a couple years. But the cameras are using custom CMOS imagers from E2V, who are now Teledyne. They just got bought out a couple years ago. Each imager is an array of 1920 by 4608. That's 1.875 by 4.5K. I didn't come up with those numbers. They're 16 microns and 3-edge buttable. So we've built the focal plane with a 2x5 array of these guys. The cool thing about these sensors, they're back illuminated, so they're 100% photosensitive. Thing with CMOS, which actually allows us to do this multiple subframe readout, as each pixel has its own readout electronics on there. But those readout electronics take up a lot of the real estate on the front illuminated pixels, so you only get about 30% coverage that's photosensitive. They're back illuminated, they're 100% photosensitive across the whole pixel. The other problem with CMOS is that each pixel has its own bias because it has its own electronics. And that bias varies with time. What people typically do is they'll read out their full frame, they'll close the shutter, and then they'll read it out again to get the bias. And we obviously don't want to do that for the 20 hertz cadence. But with the back illuminated sensors, there's room for a couple more transistors on the pixel, and they have circuitry in there which does the subtraction as you read the pixel. So it gets the bias and the photoelectrons and does the subtraction all at once. And with that, we can get the read noise down to about 3 electrons versus the 14 or 15 electrons you typically get for CMOS sensors. We've tested this. We can get up, a little bit more than 1,200 subframes per imager, but once you start getting into that area, you start to have to. There's constraints on how you space out the boxes, but I don't think we're ever going to get that many stars to begin with. So our first science result, this is with the prototype CMOS camera, was an occultation by Pluto, which passed right over San Pedro. And this was like a week after our prototype camera was delivered, and we were frantically trying to get everything going, and we managed to do it. We didn't have any guiding. Our pointing model wasn't very good. We ended up just putting a whole bunch of subframes right next to each other to read out at 20 hertz because we knew the star was just going to be drifting across the field of view. The cool thing is these spikes are real. They were also seen at the 2 meter with the EMCCD camera those you guys have. And we also did this with and/or ASIAA CMOS camera, which we had on another one of the TAOS telescopes. So these are caused by caustics in Pluto's atmosphere, causing these sharp increases in brightness, which is kind of cool. So you can see the pixels here. This is no event. This is at the start of the event. Right here, you're just looking at Pluto itself because the star is being completely blocked out. So it's always cool to do science, but this was actually a nice test. We had a signal noise of 27. Our estimate for a star of this brightness would be about 40. But as I mentioned, we had no guiding. It was a prototype camera, so it had a lot more read noise just because the pixels were smaller. So we should get pretty close to where we are. We still haven't gotten our full measurements yet. So anyway, but this was 20 hertz imaging and using the subframe readout. So that was a good demonstration that this technique will work. These are the science cameras in the lab in Taiwan. Here you can see the 2x5 array of the imagers. These things are just these little flex cables. Each imager has 100 pins. Multiply by that 10, it's 1,000 lines you got to get out of the vacuum, which is kind of hard to do with the glass to metal seals and all that. So we're just using printed circuit boards. As you can see, underneath the camera, you can see the cables connected to these boards. They just come out through the bottom through a potted flange, and they're bolted tightly in place. So, because if you touch them, then you got a vacuum leak. On the bottom of the camera, you can see the circuit board coming out through the flange here. And each imager has one of these cards, which has an FPGA controller on there. So that FPGA controller addresses the individual pixels in whatever order we choose. We can upload the window coordinates to this thing, and it will generate the pattern it needs to read everything out. For this multi-subframe readout, it reads out row by row, but it will assemble the pixel order into the subframes for each star, and then dump them over the network to our computers in the control building. So cameras drove last April, a year ago, April, and this is our obligatory first focused image of M101. But this shows the full frame here.
What is the field of view of this?
It's about 1.7 degrees. So the viewable field is a circle of 1.7.
Okay.
We think we can still just read the very bright stars up from the corners. They're going to be pretty ugly, but we'll still have enough signal noise to use them for the science. And last June, we managed to do some 20 hertz imaging. Seeing wasn't very good this night. so things are kind of moving around a little bit, but so we were able to do several hundred subframes, and yeah, we had, what did we have? We just did 10 stars per imager. We just had to manually upload the windows. So we didn't want to do 1,000 or 10,000 of those at the same time. So we need to automate that. That's something we're working on at the moment. And obviously we need to improve the collimation a little bit here too. We did that back in September for 2 of the 3 telescopes. So before we finish commissioning the survey, we got to finish the collimation. 2 of them are mostly done. 1 needs some work. We're working to finish the robotic control software. There's a lot of stuff we couldn't do until the cameras were ready, because we needed to be able to test on the sky. We have the camera controller, which is mostly done. Master calibration image generation application, we're working on that. We need to do some real-time analysis. If we want to upload these windows, we need to automate getting plate solutions and matching with the catalog. We need to be able to analyze for focus sequences, things like that. We need to implement guiding. That's actually easier for us because we don't need a separate system for that. We're imaging at 20 hertz, so we have a very good estimate of our centroid position in real time. And we did this same thing for TAOS 1, so it's not, there's no learning curve. We just have to write new software to do it. And the star selection, getting the plate solution, matching it to the catalog, finding where the stars are, and setting the window coordinates for all these stars and uploading them. Again, that's something we did something similar to that for our analysis in TAOS 1, although we didn't have the subframe readout, but we had to do that for our aperture photometry. And we also need to work on archiving. We're building a mirror of the CADC archive system here in Ensenada, and the mirror will bring the data down from San Pedro and put it on the system here, and then it'll automatically get copied up to Canada. So that's a lot of work that is ongoing now because it's a pretty complex system, and also just getting the image format. We have to get all the metadata so that it's searchable by the so the images are searchable by the database, and they'll show up in the various search criteria. So we're expecting to be in the survey early next year. A lot of this stuff should be done by the end of the year. And we plan to run the survey for about 5 years, and after which we'll see where we are and what we've learned, and whether it's worth continuing or moving on to the next thing. I apologize for all the equations here to talk about the survey sensitivity. JJ Kala, I just gave these talks in Canada, and this guy's like, I want to see those equations. So I had to screw around with Microsoft stupid equation editor for a couple hours to try to make this work. So the survey sensitivity, we use this parameter, which we call our effective sky coverage. That just comes from the nomenclature for direct surveys. If you look at the cumulative number of objects you have larger than diameter D, you have some model of the size distribution, the amount of area you cover on the sky, and then your detection efficiency, which is some function of diameter. And since this is model dependent, this is the survey dependent, they just combine this sky coverage and detection efficiency into this effective sky coverage here. For the occultation surveys, it's a bit different. It's more like a particle physics experiment. So for a given star, for a given data run, which means we'll observe a field for 2 hours, you have the flux, which is the size distribution times the relative velocity, and we do this angular velocity. So you divide by the observer T&O distance, and then you get your cross section. That gives you this velocity, and the cross section gives you your event rate. You multiply that by the duration of the data run, and then your efficiency for that diameter for that particular star and for that particular data run. If you observe the same field, it's going to be different because the moon will be at a different position. You'll be at a different elevation on the sky. So you rearrange this a little bit and you get the same integral over this times this big mess here. And so this actually put in a couple factors of 180 over pi, and you got a quantity that has units of square degrees, and it has nothing to do with sky coverage, but we call that our effective sky coverage. So to estimate the survey, people say, how many events are you guys going to get? I don't know. That's if we do that, we wouldn't have to do the survey, but we can try to guess at what the sensitivity will be and what we can expect based on different models at the site. So on the left here, we got our effective sky coverage. So this green line is what we got for TAOS 1. So one simple thing you can do is just guess like how many hours times how many stars you'll have on the sky and scale your sky coverage that way. So we expect about a factor of 300 increase over TAOS 1. That's for 5 years, 300 nights a year, averaging 5,000 stars. So that's this dashed line here. So that's not including any increase in sensitivity, that's just exposure. And as somebody asked, when I showed those sensitivity plots, though, we're actually quite a bit more sensitive to smaller objects. And so I did the math that went into those sensitivity plots and just came up with the limit, and I just shifted the curve to the left to match that limit. I'm sure it's not correct, but it's not too far off. It's within a factor of a few of what we can expect to see. So that's this solid black line here. So given this quantity, you can make a model independent upper limit, assuming you find no events at the 95 confidence level. So the question is what's your density limit? And so you find what would give you three, which is what you would doing Poisson statistics, is your 95% confidence level upper limit if you detect 0 things. So if you just take 3 divided by this curve and plot it here, that's your density limit as a function of diameter. And I say it's model independent in that any model which gives you some number anywhere above this line for your number of expected events, you can eliminate that model if you find 0 events, which is what we found at TAOS 2. And all these other points up here are other attempts at occultation surveys that people have reported. These 2 points here are reports of possible detections, which are just right at the TAOS 95% confidence level upper limit. This one was done with the fine guidance sensors on the Hubble Space Telescope. Somebody went through and looked through all the archival data on that. I don't believe it for a second. And if anybody's interested in why, I'll tell you later. This was done by a Japanese group that just had 2 30-centimeter telescopes on the rooftop at sea level in Japan, and they found something that dropped, and it was like 6 sigma drop in flux. So they said that's the occultation by TNO. I don't really believe that either. So the interesting thing here is these points here are direct detection, and this is this red dot is an upper limit from the Hubble Space Telescope survey at about magnitude 29, which you can make an assumption about the albedo, and that'll move that left or right depending on what you decide the albedo is. These are actual detections of objects, so we should be close to the regime where we can tie that in with the direct detection surveys after we run for 5 years. I expect the JWST survey to get up to about 10 kilometers, so that should give us a little bit more of an overlap. So let's look at some models here. There's 2 models that have been published in the past decade or so. The one I'm more likely to believe is this blue one, because that's based on the cratering size distribution on Pluto and Charon as measured by the New Horizons flyby. This other model was by the same people that did this HST fine guidance sensor result. and it miraculously picks a size distribution which goes right through their data point right there. So, but it's a model, and so it's just let's use it. It's more recent than a lot of the other things. So, if you recall from the last slide, you take the size distribution, multiply it by the effective sky coverage, and then integrate up from infinity up to your diameter, and that gives you the number of expected events with diameter larger than d. So for the cratering size distribution result, this dash line is using the conservative estimate, the blue line is using the taking into account estimate of the increased sensitivity of the survey. Again, 5 years, 300 nights, 5,000 stars. We should find a few hundred events, up to maybe 1,000 events over the 5 years. And with using this other model, we can expect quite a few more. Now, again, I'm not claiming that this is correct, but if it's within a factor of 3 or 4, we should find hundreds of events through this survey if any of these models are correct. And this is Goel's work, just a little caveat I should mention. All these results are assuming the objects are perfectly spherical. So every faint TNO that has been directly imaged and with any resolution at all one of them, Arikoff, which was imaged by New Horizons during the flyby a couple years back. It's a compact binary. So if you extrapolate 1 to the whole population, then every TNO is compact binary. And it's actually not an outrageous estimate, simply because a lot of the formation models are predicting things either formed as binaries or compact binaries. So that actually affects the diffraction pattern. Now, interestingly enough, I should mention we have this parameter called the effective diameter. That's because compact binaries do not have diameters. So some sort of size scale to compare spherical versus non-spherical. So we just look at the projected size, get the area, divide by pi, and get the radius that way. So interestingly, when you're very small, much below the Fresnel scale, it doesn't really matter. You get a little bit of asymmetry, but the patterns look pretty much the same. These lines here are different chords at different distances from the center. It doesn't really look that different. When you get up to 3 kilometers, the pattern gets a little wonky for sure. Doesn't look too different here. This Poisson spot, when you actually get 2 Poisson spots in this one. And once you get out to about 2 kilometers, at least in this orientation, you don't really see much of a signal. I certainly wouldn't say, hey, we found an occultation here. Obviously, if they're moving this way vertically, then you got different chords. When you get out to the geometric regime, you're still seeing the wings at some point. Here on this bottom one, it's actually going across this cusp. So you see 2 drops plus these bright points in the middle. So we can model this. The problem is that these are very computer intensive to calculate. With the spherical ones, you just do a radial profile and you can rotate it around. It's axially symmetric. This one, you need to calculate the full 2-dimensional diffraction pattern. So it goes as n squared instead of just n. We can't really do the full analysis with this. So our plan currently is just to pick a subset of shapes and sizes and look at how it affects our detection efficiency and how it biases our estimates of the size. So this is another project that needs doing. Let's talk a little bit about the data. So this is a model we have for our for TAOS 1, and then these are some of the data points we measured. This is signal to noise versus magnitude, and that model's fairly accurate, and it's good enough for our purposes here. So, and I apologize, this is an old plot, but this is the model we did for TAOS 2. Unfortunately, this was an earlier estimate of our read noise of about 2.4 electrons per pixel. It's now closer to 3. So that's gonna turn this cutoff down a little bit before 18. So we're estimating about somewhere around 17. And when I say around 17, I'll say between 16.5 and 17.5 in magnitude. So these are the stars that we will have data for. So I mentioned this before, a data run, we're just calling that a collection of multiple subframe time series data on a single field from 3 telescopes at 20 hertz. And we'll have a typical run length of 2 hours before we just stop and then pick another field. And we'll have an average, we're hoping around 5,000 stars and about 4 or 5 runs per night, 300 nights per year for 5 years. And then we're going to define a light curve set as a light curve for a star, but taken for 3 telescopes over one of these 2-hour data runs. So in 5 years, we expect to have about 37.5 million of these light curve sets. We'll have 8 trillion photometric measurements, and that would be on 3 different telescopes. So simultaneous measurements will have about 2.7 trillion photometric measurements. In addition, we'll be taking full frame images of the field before we start a run, just to find the stars, maybe adjust the telescope pointing to maximize the number of stars where we have a window on all 3 telescopes. And we'll take a few after we finish a run as well for diagnostics. So we expect about 70,000 of those frames. And that will come to about 3 petabytes of image and light curve data. As a bonus, we have these telescopes came with finder scopes on them. And I don't know if anybody uses a finder scope anymore to try to tweak their pointing to center their telescope on whatever they're looking at. But they're about 6 inches. 6 inches. What's that? That's about 15 centimeters. Okay, 15 centimeters. So we got some small cameras for these things, and we want to have images of the full field of view. If something goes on and we only have little windows going around, we won't really know if there's something strange happening in the whole field. So our plan is to just take 30-second exposures with these telescopes. So we'll have, as we're collecting this window mode data. So we expect around 4 million of these images by the time we wrap up in 5 years. And thing is that with the CMOS cameras, for the science cameras, we actually found there's a trade-off between well depth and read noise. We opted for the lower read noise. So our well depth is quite a bit smaller than what you would expect for CCDs. So we're going to saturate around magnitude 12 or so. So this would be good for looking at some of the brighter stars for some of the other science that might possibly come out of this survey. So just how the data will be formatted. So we got 3 cameras at 3 sites with 10 imagers. So our plan, we got 10 servers in our control building, and the plan is to have each one look at the same imager on all 3 cameras. So all the data from one part of the sky from the 3 telescopes will go to one server, and they'll be stored in the same data file. So we'll have 3 images for the full frame. We'll have 3 full images in each data file from one portion of the camera. For the window mode data, we're going to have a separate file for each star, and so that star will have an array of 3 postage stamps in each file. So the data will be, if it's a 9x9 window, we'll have 144,000 by 9x9 data cube times 3 for the 3 telescopes. So we're going to store our image and light curve data in HDF5. There's a couple advantages to that. There's no byte swapping. We don't need to put it in big Indian format, so we can swap it back when we read it in again. It's not a huge thing if you're not doing that many images, but for our analysis, the IO we found was a big driver in the amount of CPU time it took for TAOS 1. And it's easy to deal with. It's self-documented. There's no separate schema that you need for ASDF. There's no punch card based limitations on 80 characters per record for your metadata. It's easy to organize. It's hierarchical format. You can put it in it's like a file system. You got directories and files, which are called groups and data sets in HDF5. You can define your own compound data sets, so you can write C structures directly to the file and read them back in. You've got attributes, which we use for units for our metadata. But the main reason we're doing this is for this idea of chunked output. We're going to have up to 1,000 open files on each server and collecting all this postage stamp data. And we can't buffer all that and then write it at the end. So we're gonna have to write out chunks of the data multiple times throughout this 2-hour data run. That's going to be a real pain to do with things like fits. We'd have to be, moving around the disk to put things and hope that the spacing comes out correct. But with HDF5, you can just write a full chunk and it doesn't have to be contiguous on the disk. It can just be scattered around the file, and the library and the metadata inside the file itself keeps track of where these chunks are. And furthermore, you can compress these chunks as you write them. So it's actually much better for what we're trying to do. And it's also very fast. It's much more efficient than CFITS.io. You don't have to parse strings to get your metadata in. You save your metadata in the native binary format. And it's pretty easy to use. If you're using PyFits, it's the same thing. You just open the file and it's there. So I'll skip that. And so the main thing I'm here is we're going to have this data set. It's going to be very cutting edge and very unique. And we've put a lot of time and effort into making this data set. And we'd like to maximize the output, scientific output from the use of this data set. So that means doing things other than the occultation survey with this data. So I'm in the middle of a grand tour of all of our collaborating institutions, trying to get other people interested in some possibilities. So currently we're going to open up the data to our participating institutes, ASIAA, UNAM here, and CFA, and in Canada. And we want to encourage people to work together among the different institutes, even if it's something completely unrelated to occultation stuff. We will eventually make this data publicly available. That's more or less becoming required from funding agencies, at least in the US and in Canada. I don't know what the rules are in Mexico about that, but anything that's federally funded data has to be made public at the time of publication. But in the short term, we expect that people who are using the data will need to work with the core science team. We have a lot to learn about this data set. There's going to be a lot of things we don't expect in there. There's going to be features that we don't understand and need to explain. And if we just make it publicly available to everybody, people will probably misuse it, and they will probably come up with erroneous results. I have experience with that myself. As a member of the Macho collaboration, we made the data public. People published papers. We had to write another paper saying why it was wrong, because they didn't pay attention to some of the things they're supposed to pay attention to. So it's, so not only is it our interest to get the science out, but it's our interest to have other people looking at the data, because if we get some feedback, some back and forth, we can learn about some of the weird, unexpected things that are in the data set, and we can set up some quality checks, flag some bad data, understand if there's some weird patterns that are showing up that we don't understand. We can try to figure out what they are. So just some of the suggestions we've had, just talking to various people, and the experience we had from TAOS 1, other science we got out. So there seems to be a lot of interest from the exoplanet people. I know some people here have done some modeling of what transit events might look like in the TAOS 2 data set. And I just was in Canada earlier this week and gave 3 different talks there, and the people at TESS are very interested in that as well. I was unaware of this, but their pixel size is 21 arc seconds. So if they find a transit, then they're not sure if it's, how many stars are in there and which star the transit's actually occurring. So they'd be really interested in looking at our data, just if they can see which star the transit happens in, and also try to get a better handle monitoring the transit timing. Variable stars, we actually had more variable stars in TAOS 1 actually get cited more than our occultation result papers. I'm hoping that'll change if we actually detect some events, but and this is also the same with my experience in the Macho collaboration. I don't think it was more, but it was very close to the same number of citations. And with TAOS 1, we discovered at the time like 40% of the known Delta Scuti stars that were known. This high cadence data is really good for finding those. We also had full frame images with TAOS 1 from the science cameras, so we'll have that for the finer scope cameras and the science cameras here. And we're going to be looking at roughly the same field as TAOS 1, so we can actually look at data we had from 15 years ago and compare it with what we have in the future here. There might be some interesting objects. We're looking at our fields for cataclysmic variables. If there's any bright quasars, I'm still a little skeptical that some people think we might be able to see something interesting here. And also, if there's any really interesting objects people are, would like to look at, we can, if it sounds cool, we can make a new TAOS field that includes that object. So we'd like to stay close to the ecliptic and where we expect most of the TNOs to be, but we can, if there's anything worth looking at that you would like to see at high cadence, we can do this. Some people are talking about stellar seismology. That's beyond my pay grade, but a lot of people might be interested in the high cadence data. Some people at the CFA are interested in the atmospheric effects, looking at correlations in the light curves between nearby stars with time lags, correlations between the different telescopes. It's mostly like AO people who are would be interested in learning what they can about that. So, and then we're planning to have a workshop. This is my appeal to get people to join so we can get a free trip to Mexico. So it's going to be in spring of 2025. People May. We don't want to be up there when it's snowing. I just came from Canada, so I had to clarify that BC, Baja California, and not British Columbia. So, but this would be a good opportunity to meet scientists from Taiwan and from the CFA and from Canada. And, I'm here. I'm sure you guys all know each other, and meet some potential collaborators if anybody has any similar scientific interests, or maybe you might hear some talks and not realize you're interested in something that I would like to collaborate. And for people who are interested, we're even going to have an SPM site visit. So I know Anna would like to go. And we're probably going to have our first light kickoff party as well. So we're going to be invited to that as well if you decide to crash the workshop. So I will end it there and take any other questions.
Any questions? That's
I don't think you serve 5,000 stars per year.
No, at a time.
I need that. Okay.
Yeah.
You will come. You will serve one field. You come to the same field or different field?
We'll observe a field for 2 hours and we'll pick a different field. We'll try to stay near zenith, but we'll have to move around a little bit if like the moon is full and it's up more, Jupiter's in the field, because that'll wash out all the stars. But on consecutive nights, we'll likely visit a lot of the same fields. So then a year later, we'll come back to the same group of fields.
So how many different fields do you have defined?
Currently, we have about 165.
That's not too many. So you come back to the same fields.
Yeah, we have a few that are off the ecliptic. And that is mostly they're just kind of hugging the edge of the galactic plane. We don't really want to go in there because it's just too much too much background and too much stuff. So if that's the only thing visible, we'll move off the ecliptic for a bit.
I have a question about the data you mentioned. After the data is analyzed, are you planning to give some periodic releases of the data along the 5 years or after the?
Yeah, so I mean, so for any project funded in the US and I believe Canada as well. And at the moment, I don't have US funding, but I'm hoping to get some. But the rule is that as soon as a paper is published, you have to release the data.
Okay.
So that can mean different things, right? So if somebody is looking for variable stars, you know, they can just release the variable star data, right? And that would be fine. If somebody wants to look through the whole data set for something weird, maybe we'd like to hold off until we have our first occultation survey paper ready. If there's an interesting object, they can just publish the data for that object and we can make it public. So with the CADC thing, you could just make a date to make it public, and then you could just change that date and make it immediately. It just immediately becomes public. It shows up in the search. So it really depends on the science and what people are doing.
We have one question on Zoom, William Lee.
Yes, hi, William.
Hey, can you hear me?
Yes.
Hi, Matt.
Hi.
Thank you. So I have a question. How much degeneracy do you have in terms of size and binarity? Because as you said, in the non-binary models, you just do a radial calculation and that's it.
Yeah.
And in the others, you have to do the full 2D diffraction pattern. But how much of these shapes are affected? How much are they affected by the orientation, and do you get any degeneracy between the size and binarity argument?
That is unknown at the moment. That would require just a pretty large survey, or not survey, simulation and analysis. I mean, the patterns are identical, starting a little bit larger than a kilometer as you get smaller and smaller.
Mm-hmm. Mm-hmm. Yeah.
And then it really just depends on the shape of the object. And it depends on the orientation of the object. So I couldn't really say how much degeneracy there is or how similar they might look. And
Okay.
and it's, you know, we're working on fitting. We also have some instead of trying to fit compact binary light curve, which is, you know, there's just an infinite number of parameters. As I mentioned, the width sort of roughly goes as the distance to the object, and the depth goes as the diameter. So we have some shape parameterization to try to get the width and the depth. And
Okay.
working on that and we need to improve it a little bit for larger objects because that the depth is always 100%. You're out of the diffraction regime at that point. But
Mhm.
just a rough shape parameterization I think could help us out as well.
Right.
Instead of trying to look at the size distribution, you can calculate the shape parameter distribution from your model and then see how that compares with what you measure.
Mm-hmm. Okay. Thanks.
Question
Yeah.
about the stars contained in each field. So are these stars already characterized? For example, knowing the astrometry from Gaia, for example. the
Every
physical
star
parameters?
we're looking at is in the Gaia catalog. So
Okay.
we use the Gaia catalog to find our aperture. So we'll use astrometry.net and S extractor for this new thing called Stellar Solver, which combines the two. And one of the guys here is actually working on that. But you get the plate solution, and then S extractor will find, you know, only the brighter stars, but then we'll use the Gaia catalog to define the apertures for all the other stars in the field. And for TAOS 1, we did that for the analysis. We would find the brightest stars, guesstimate the point solution from that, and then plunk our photometry apertures down on the stars. So that worked really well in the past. Although there was no Gaia, we used the GuideStar catalog. So, but yeah, every star we have is in the, will be, we have our own catalog database, but that's all data we pulled from Gaia.
You will serve any type of the star. Or you
Yeah, we
prefer-
observe all stars. It's,
No, I mean,
Yeah.
every fractal type or there is
Yeah.
a preference now.
yeah, I mean, we thought about that, but then I was like, well, I mean, the alternative, I mean, the stars are what's there, so we can either pick it or we could just observe every star. So we're just gonna observe every star and stuff, and hopefully something useful.
The catalog is going to have only instrumental magnitude or kind of calibrated magnitude?
It's a good question. I mean, it really depends on, you know, what is useful is. I mean, is it worth the time and effort to calibrate every star on the field? You know, then you have to take care of all that, dome flats and things. We have screens for dome flats. We have plans to take them, but it's a question of how, you know, our field is, has a short pass filter, so we're, going from roughly where the QE drops to 0 at 400 nanometers up to about 720 nanometers. It's not going to be, so it's going to, the TAOS magnitude won't super closely correlate to any particular pass band.
Okay.
So now if it's useful to have that, we can certainly go through the trouble of doing it. It wouldn't be that hard, but you know, but on the other hand, if it's only for the interesting objects, maybe it's easier just to calibrate those. Yes.
This may be a very stupid question.
There's no such thing.
I'm an expert in stupid questions. Now, there have been many surveys looking for this stochastic computations.
Yes.
Starting with machos and TAOS and everything. But have some of these other surveys have found Transneptunian object occultations?
There are 4 that have claimed detection. So one was this fine guidance sensor survey. I'll just go on my rant about that. So I don't know how this paper got past the referee, but the fine guidance, the Hubble pointed everywhere, right? So most of the TNOs, they expected to be below 30 degrees latitude, ecliptic latitude. They found 2 events there. And they had about a third of the data, 2/3 of the data was in this region. And then above 30 degrees, they had a section of the paper called high latitude control sample. And they found an event at 80 degrees latitude and said, this is too high of a latitude, so it's a false positive. And that was the end of the discussion. So a third of the data had 1 false positive. 2/3 of the data had 2 events that they claimed were real. That seems like they have 2 false positives in their data set. So the one is the Japanese guys that claim they found an event because there was a 6.4 sigma drop in the flux on 2 telescopes that were pretty close to each other. And they did the Gaussian statistics and said it was 10 to the -10 probability. But if Gaussian statistics don't work that far out on the tails, and they played this trick where they plotted their noise distribution over a Gaussian, but it was on a log plot, which makes it look a lot closer together than it is. And if they did just zoomed in on the tail in the linear plot, there would have been a huge tail above the Gaussian. So that doesn't really preclude them being correct, but if you got 2 telescopes and they're pretty close together, we saw in TAOS 1, we had 2 telescopes that were really close together and others that were further apart. We saw a lot of like coincident drops on the light, in the light curves that we didn't see on the other two telescopes. The third one was another guy who just with one telescope found a 10 sigma event and decided that that was too far off in the tail, so it must be an occultation. And the other more interesting one was this, these guys looked at the archival RXTE data. So it's in the X-ray. So the Fresnel scale is very, very tiny. So there's no diffraction there. So you get these nice deep flux drops. And they found a whole bunch of them. And they were a little more, you know, put some caveats on that. They weren't claiming we found occultations, but they published it. And I was at the CFA at the time, and then we, you know, MIT, which ran this thing, was just down the road. So we told them about the paper, and they hadn't seen it, and they decided to have they called us down for a meeting. And so it turns out with these X-ray detectors, every once in a while you get some really big event which drains charge from your preamp, which puts these little dips. And for half of the events, they found one of these really big events right before this occultation event. The other half, they didn't have the data whether one of those things occurred or not, but it was not a good sign for that. But none of them have used, only the Japanese guys used more than one telescope, but they're very close together.
And also, how would you distinguish, well, an exoplanet occultation from you know,
Well, exoplanets,
or eclipse in binary?
yeah, exoplanets would last way more than any of those things would last way more than a fraction of a second.
Okay.
And I also mentioned, like, you know, it would help if we have a lot of events. Because I mean, I'm skeptical of any claim. I'll be skeptical of anything we claim as well, which is only fair. But there's a couple things, like if we have high enough event rate, we can move off the ecliptic, and we should see the number of detections drop with ecliptic latitude. And also we can, since we'll be looking, you know, at zenith as much as possible, we'll cover a range of opposition angles. And so at larger opposition, the relative velocity is smaller. So we shouldn't really see any short duration events as we move away from opposition. So there should be sort of an excluded region where there's no events if we plot event duration versus opposition angle. And if we can find that significant correlation to that, then we can tie in our results to the position of the sun behind the Earth, which would tend to indicate it's a solar system origin and not something else.
Another question here. Question Zoom. Let's see. Nice. Okay. Bueno, demos las gracias de nuevo. Okay.